If you're serious about resistance training, I mean, really serious, you're always looking for that edge, right? Trying to understand how to optimize every workout, hit those goals. But what if you could like actually see inside your muscles during a set, understand how they're responding in real time? Okay, let's unpack this. Today we're doing a deep dive into some really fascinating new research. It sheds light on exactly what's happening with muscle oxygenation during back squats, specifically how things like the weight on the bar and how much your bar speed drops off affects those oxygen levels. And this isn't just, theory. It's about making your training smarter, more tailored to you. So the paper we're looking at is titled Muscle Oxygen Saturation Dynamics During Back Squat Exercise: The Influence of Intensity and Velocity Loss on Deoxygenation and Reoxygenation. Quite a mouthful, but important stuff. It's by Shih-Hsuan Chen and several colleagues: Chiang, Tsung-Lin, Chen, Su, Hsuan-Yun, Wang, and Huey-June. Published just recently, well, slated for 2025, in the Journal of Sports Science and Medicine, Volume 24, pages 555 to 564. And the core question they're asking is, how do different mixes of training intensity and this thing called velocity loss impact oxygen in your muscles during squats? And crucially, why should you care for your training?
Well, it matters because traditional resistance training, the kind based purely on a percentage of your 1 rep max, your 1 RM, it can be a bit inconsistent.
Yeah.
Yeah, I mean, two people could be lifting, say, 70% of their max, but one might be fatiguing way faster than the other. There's just a lot of individual variability.
Right, so that percentage doesn't always tell the whole story about the actual effort or fatigue.
Exactly. And that's where this newer approach, velocity-based training, or VBT, comes in. It's seen as a more individualized solution. VBT basically uses how fast you move the bar as a real-time gauge of fatigue. You track the velocity, and when it drops by a certain percentage, that's the velocity loss, or VL%, you stop the set. It lets you adjust the volume dynamically based on how you're actually performing right then and there.
So it adapts to your fatigue level on the day?
Precisely. And previous research has shown it's pretty effective. Maybe a 10-20% velocity loss is good for performance goals, while going higher, maybe over 20%, might be better for hypertrophy. And the study uses a cool non-invasive tech called NIRS, near-infrared spectroscopy, to measure muscle oxygen saturation, or SMO. What's fascinating here is, how this study really connects the dots between VBT principles and what's physiologically happening with oxygen inside the muscle tissue itself.
Okay, so NRS lets them peek under the hood, so to speak. How did they actually set up the experiment to do that? What was the design? They used a really solid design, a repeated measures study. That means every participant did every single one of the different squat conditions. That helps control for individual differences. And who are the participants? They recruited 18 guys, all resistance-trained males. Average age was around 20. And they weren't new to lifting. They had between 1.5 to 3 years of experience, so they knew how to squat properly. To keep things consistent, they had everyone perform 4 different back squat protocols, but on a Smith machine. This helps control the bar path. These 4 protocols were combinations of different intensities and velocity loss targets. You had 60% of 1 RM with a 20% velocity loss, let's call that 60-20. Then 60% 1 RM with a 40% velocity loss of 60-40. Then they up the intensity, 80% 1 RM with 20% velocity loss, that's 80-20. And finally, 80% 1 RM with 40% velocity loss, the 80-40 condition. 3 sets for each protocol, with 5 minutes rest between sets.
And for the measurements, they use 2 key tools. First, a GymWare device. It's a linear position transducer attached to the barbell. That tracked the bar velocity very accurately, so they knew exactly when the target velocity loss, whether 20% or 40%, was hit for each set.
Okay, so that handled the VBT side of things.
Right. And second, for the muscle oxygen, they used a Moxy-Monitor NIRS device. This was placed on the vastus lateralis, that big muscle on the outside front of your thigh, and it continuously measured SMO throughout the sets and rest periods. SMO basically tells you the balance between oxygenated and deoxygenated hemoglobin in the muscle capillaries. It's a real-time look at how much oxygen your muscle has available.
Got it. So what specific oxygen variables were they tracking with that Moxy monitor?
Yeah, they focused on 3 main things. First, the magnitude of the SMO row decline, basically. How much the oxygen saturation dropped in total from the start of the set to the end. Second, the slope of that decline. So how fast the oxygen level was dropping during the exercise itself, the rate of decrease. And third, the SMO recovery slope, how quickly the oxygen saturation started bouncing back during the first 60 seconds of the rest period after the set finished.
Okay, magnitude, decline speed, recovery speed. Makes sense. So with all that set up, what did they actually find? What did the data show? Was there a difference in how much oxygen dropped?
Well, this is where it gets interesting. Despite those four different conditions, different weights, different velocity loss targets, they found no significant difference in the total magnitude of SMO decline.
Wait, really? So lifting heavier or stopping sooner didn't change the total oxygen drop?
Not significantly, no. Across all conditions, all sets, the SMO consistently dropped from the starting point down to a range of about 47% to 58%. So the muscle seemed to reach a similar level of deoxygenation regardless of the protocol.
Huh. That's kind of counterintuitive.
Yeah.
I would have thought 80% would cause a bigger drop.
You might think so, but the total drop was similar. Here's where it gets really interesting, though. The rate of that drop was very different.
Ah, okay. So it wasn't how much it dropped overall, but how fast it got there?
Exactly. The speed, the SMO decline slope, was significantly steeper, meaning oxygen dropped much faster, specifically in the 80-20 condition. Compared to both the 60-20 and the 60-40 conditions, that 80% intensity combined with only a 20% velocity loss led to a much more rapid deoxygenation.
How much faster are we talking?
Well, the numbers show it was considerably faster. For example, the slope for 80-20 was around -1.7 to -2.0% per second, whereas for 60-20 it was more like -0.8 to -1.1, and for 60-40 it was even slower, maybe -0.5 to -1.0% per second. So yeah, much quicker oxygen use or slower delivery at 80-20.
Okay, that makes more sense. Higher intensity, faster oxygen drain, especially if you stop the set relatively early based on velocity. What about the reps performed? Does that line up with what you'd expect?
Yeah, the rep counts followed a predictable pattern. As the intensity, the load went up, the number of reps participants could do went down. And the 60-40 condition with the lighter weight and the larger allowed velocity drop generally resulted in significantly more reps compared to the higher intensity 80-20 and 80-40 conditions. No real surprises there.
And what about getting that oxygen back between sets? Any differences in recovery? On the recovery side, looking at that initial 60-second SMO recovery slope during the 5-minute rests, there were actually no significant differences between any of the conditions. It suggests that the early phase of reoxygenation happened at a pretty similar rate, regardless of how demanding the previous set was in terms of intensity or velocity loss.
So what does this all mean? If I'm listening right now thinking about my squats, what's the big takeaway from this difference between the total oxygen drop being similar, but the speed of the drop being so different? Well, that consistent magnitude of decline where SMO seems to hit a similar floor, around maybe 50-something% saturation. It's really interesting. It suggests your muscles might have some sort of autoregulatory thing going on, like they hit a certain low point of oxygen and mechanisms kick in, maybe increased blood flow, opening more capillaries to prevent it from dropping much further.
Like a built-in safety mechanism or a limit?
Sort of, yeah. Or maybe just a physiological threshold. It implies that the trigger for stopping the set or the fatigue point related to oxygen might be reaching this threshold, rather than just the total amount of work or reps done. Now, thinking about specific protocols, the 60-40 condition stands out. Remember, it had the slowest rate of SMO decline.
Right, the oxygen dropped more gradually. Why is that potentially beneficial?
Because it means the muscle spends a longer duration in that hypoxic or low oxygen state during the set itself. And we know that this kind of extended time under tension, specifically in a hypoxic environment, can be a potent stimulus for anabolic signaling. It could potentially lead to better muscle growth, maybe especially for those type I, more endurance-focused muscle fibers.
Okay, so for hypertrophy, maybe drawing out that low oxygen state with moderate weight and higher reps, like in 60-40, could be a good strategy.
It seems plausible based on this data, yes. It prolongs the stimulus.
You also mentioned the rate of oxygen decline was particularly sensitive to the velocity loss percent at the higher intensity, right? At 80%.
Yes, that was another key finding. At 80% of 1 RM, changing the velocity loss from 40% down to 20% made a big difference in how fast the oxygen dropped. The SMO rearose decline slope was much steeper with the 20 per state VL. But at the lower intensity, 60% 1 RM, the difference in the decline slope between 20% VL and 40% VL was much smaller, less pronounced.
So the velocity loss target seems to matter more for oxygen dynamics when you're lifting heavier.
It appears so, based on this study. It suggests that how early you cut the set based on velocity has a greater physiological impact, at least in terms of oxygen kinetics, when the load is high.
Okay, let's translate this into practical advice. How could someone listening use this information to structure their training?
Okay, well, if your goal is maybe maximizing the training stimulus efficiently, getting a strong physiological effect without necessarily doing tons of reps, then that 80-20 protocol looks interesting. It causes that very rapid, steep drop in muscle oxygen. It's demanding, requires fewer reps, potentially very time efficient for delivering a potent stimulus.
Get in, hit it hard and fast, physiologically get out.
Kind of, yeah. But if your main goal is hypertrophy and you're willing and able to push through longer sets, then the 60-40 protocol offers that benefit of prolonged time under hypoxic conditions, which, as we said, is thought to be really good for signaling muscle growth.
So different tools for different goals, essentially, based on how you manipulate intensity and velocity loss.
Exactly. It provides a physiological rationale for choosing different VBT parameters.
Now, we should be fair and mention the limitations. Every study has them. What are some things to keep in mind here? Definitely. For one, they only measure the vastus lateralis. Oxygen dynamics might be different in, say, the glutes or hamstrings during a squat because muscle fiber types can vary.
Good point. Different muscles, different responses, potentially.
Also, the participants were all young, healthy, trained males. So, we need to be cautious extrapolating these exact findings to, say, untrained people, older adults, or females without more research.
Absolutely. Population matters.
And while SMO is super insightful, it's not the only thing contributing to fatigue. They didn't measure intracellular stuff like inorganic phosphate buildup or pH changes, which also played big roles.
True, it's one piece of the fatigue puzzle, albeit an important one revealed by NIRS. And that points towards future research, right? Combining SMO measurements with other markers like EMG or those metabolic byproducts you mentioned could give an even clearer picture.
Yeah, and testing these protocols in different groups of people, looking at long-term training adaptations over weeks and months, not just single sessions. Lots more to explore.
Definitely. There's always more to learn.
So to kind of wrap this up, the big takeaway seems to be that when thinking about resistance training, especially with VBT, it's not just about the total oxygen drop in your muscles, which might be surprisingly consistent, but really about the rate, the speed at which that oxygen desaturation happens.
That rate seems to be much more sensitive to the combination of intensity and velocity loss you choose.
And understanding that can help you tailor your workouts more precisely, whether you're aiming for time-efficient stimulus with something like 80-20, or maybe maximizing hypertrophic signals with the prolonged hypoxia of 60-40.
It adds another layer of understanding to programming.
Absolutely. If this discussion has piqued your interest, we strongly recommend you check out the full article. Again, it's by Shih-Hsuan Chen and colleagues in the Journal of Sports Science and Medicine. You can really dive into the data yourself. And of course, make sure you follow the Deep Dive channel, turn on those notifications so you don't miss our next exploration. We'll keep bringing you these kinds of insights to help you stay